At last, the final section and the final notebook of Calculus 2. The topic here is Taylor series and Taylor polynomials. What is a Taylor series? It's a series obtained by taking the derivatives repeatedly. And it is based upon this theorem here, Taylor's theorem. It goes like this. If a certain series has a power series expansion, kind of like this, summation n is running from 0 to infinity, an x minus c to the nth power within a certain radius of convergence, then the coefficient an can be calculated by this formula here. Nth derivative evaluated at x equal to c, the center, over n factorial. And this theorem can be applied whenever a certain function has a power series expansion. For example, if we have different types of power series expansion, just like the power series expansion we saw before in the previous section, kind of like these, coming from geometric series, can we apply Taylor's theorem to get these coefficients? For example, can we actually get 1, negative 1/2, positive 1/3, negative 1/4, and so on for log of 1 plus x by taking a derivative repeatedly? Yes, you can. It's a very tedious job to take the derivative repeatedly, but it is possible. For arctangent, it's going to be even more tedious thing to take the derivative repeatedly to get the coefficient 1, negative 1/3, positive 1/5, negative 1/7, and so on and so forth. But it is possible. I never said this Taylor's theorem is practical formula. In terms of theory, on the other hand, this is very useful because it gives you a mechanism to find out the coefficient whenever a power series exists. In a previous situation, which I just showed you, it was possible to find out ANs from geometric series, so there was much easier way to find out AN. But let's suppose a situation where we know a certain function has a power series expansion, but you don't know what those coefficients ANs are. In that case, here's the mechanism. Take the derivative repeatedly and plug in the center value x equal to c over n factorial, and you have all those n values. And if you rewrite all those ANs by nth derivative of c over n factorial, we have something like this, and then equivalently we have something like that. Those kind of things are called Taylor series or Taylor series expansion. However, in reality, Taylor series expansion is no different from power series expansion that we studied before, except that it works for arbitrary series that has power series expansion. Now, how do we prove it? Well, it goes like this. Let's begin with a certain function which has a power series expansion like this, and let's take the derivative. What do we mean by taking the derivative? Here's its original function, and a0 is a constant. If you take the derivative, this will be gone, and we'll have to start from n equals to 1, which is this series over here. Now, if you take the derivative again, then the very first term, a1, will be gone, and then you have to start from n equals to 2, and that's going to be this series after taking the derivative. If you take the derivative again, then n equals to 2, this will be constant. So this is going to be gone because this is constant. And then the next series will begin from n equals to 3, and so on and so forth. And if you look at the each entry, then by derivative rule, n comes out as coefficient and subtract 1 from the power. So it's a derivative. After that, another n minus 1 comes out and subtract 1 from the power. So it's the derivative rule again, just applying the power rule over and over again. Now, if you plug in x equal to c, then basically you're plugging in x equal to c over here. You're going to get c minus c to the nth power and c minus c to the n minus first power. You're creating a bunch of zeros here. C minus c to the n minus second power and so on. Here are the computations, as a matter of fact, to help you see this. F of c over 0 factorial is calculated like this. 0 factorial is 1, so you don't have to meddle with the denominator. All you have to do is plug in x equal to c, and c minus c is 0, so all you get is a bunch of zeros here. All these are zeros, and we only have the first term, a0. How about the first derivative over 1 factorial? Again, 1 factorial is just 1, so you don't have to meddle with the denominator. And the derivative is something like this, and the series begins from n equals to 1, as I said early on. And now, plug in x equal to c, we have 0 to the n minus first power. So all these are zeros, and then we only have the first term, 1 times a1, which is a1. How about the second derivative over 2 factorial? Well, this time 2 factorial is non-trivial, so we have to keep it. And the derivative goes like this. From here, just multiply n minus 1 again, and then subtract 1 from the power, so we have that. And plug in x equal to c, we get c minus c. Bunch of zeros again. Only the first term will remain because all these are going to be 0. And what do you get? 2 times 1 over 2 factorial times a2. We have a2. Do it once more? Well, here it is. Take the derivative once again, and then over 3 factorial. From the previous entry, n minus 2 will be multiplied up front, and then subtract 1 from the power. We might have this n minus third power. Plug in x equal to c, what do we get? We have c minus c, that's 0. So we have a bunch of zeros again. All these are 0, except for the very first term. We have 3 times 2 times 1 over 3 factorial. 3 times 2 times 1 over 3 factorial times a3. We have a3. And the pattern continues, and you can easily see that this identity over here is true. If you want really precise proof, you can use mathematical induction to complete the proof. Now, what are typical applications of this Taylor's theorem? Well, let's apply Taylor's theorem to 3 well-known functions: e to the x function, cosine x function, and sine of x function. And let's just apply the derivatives using the brute force computation. Exponential is easy because derivative computation is easy. We have just e to the x all the time, and plug in x equal to 0, then we have e to the 0 power. So the numerator is always 1. So coefficient is 1 over n factorial. We can easily find out something like this. And then if you rewrite into this dot 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 form, we have something like this. I'm going to leave the students to check the interval of convergence is negative infinity to infinity. You can use the ratio test, and you can easily see that no matter what x value you get, the limit of the ratio is heading towards 0, which is always less than 1. You can do something similar to cosine function and sine function. The derivatives are not as simple as exponential, but pretty close. Cosine gives you negative sine, and then negative cosine, and then positive sine, and then back to cosine, and the pattern continues. So the derivative computations will not be too difficult. Plug in x equal to 0, then whenever you have sine of 0 is 0, and whenever you have cosine of 0, positive 1, negative cosine of 0, we have negative 1. So we have alternating signs. Same thing goes for sine function. And the detail is left to the student. It's tedious, not difficult. But remember the end result. Cosine function has alternating signs and all the even powers and even factorials. Sine functions have alternating sign, plus minus, plus minus, plus minus, and all the odd powers and odd factorials. So those are Maclaurin series expansion for exponential, sine, and cosine. By the way, the name Maclaurin, you can study what Maclaurin did and what Taylor did from internet, I think, Wikipedia or something like that. They both studied something similar, but Taylor's result was far stronger, so all the fancy things are related to Taylor. Taylor theorem, Taylor polynomial, Taylor approximation, things like those. And these three series are associated to Maclaurin series expansion. And in reality, in calculus 2 level, those Maclaurin series expansions are most useful and they are more readily related to exam level problems. Okay, now let's move on to, let's have a little bit of digression, by the way. This is such a beautiful result that I'd like to share it with you. In the Maclaurin series expansion of the exponential function, replace x by ix, where I is a imaginary number, where I squared is -1. If you do that, then you have something like this. We have ix and ix squared, ix to the third power, and so on and so forth. And then what is I? I is an imaginary number. I squared is -1. I cubed is -1 times I, so it's -I. I to the fourth power is -1 squared, so it's +1. I to the fifth power, 1 times I, so back to I. So we have the pattern. So what we end up with, we have something like this. 1i, -1, -I, 1i, -1, -I, and so on and so forth. So if we rearrange all this sum, yes, we can do that because the interval of convergence is -infinity to infinity. So everything converges absolutely here, no matter what x value we have. So the rearrangement is okay. The real part turns out to be all the even factorials and even powers with alternating sign, plus minus, plus minus, plus minus, and that's cosine. How about the imaginary part with I? We have alternating sign, plus minus, plus minus, plus minus, and so on, and all the odd powers and odd factorials. That's sine. So what we have, this result, e to the ix power is equal to cosine of x plus I sine of x. Here are some applications of Euler's theorem. Again, this is a bit of a digression, but it's such a beautiful result that I'd like to share it with you. Here, plug in x equals to pi. We have e to the I pi power, and then we have cosine of pi, which is -1, and sine of pi, which is 0. In the end, oh, not this one. In the end, we're going to get something like this. Here's the proof, by the way. Plug in x equals to pi to that Euler's theorem, and sine of pi is 0, cosine of pi is -1. So after a little bit of algebraic manipulation, we have this. E to the I pi power plus 1 is equal to 0. And this one was recently voted as, I think, the most beautiful theorem in mathematics. Well, okay, I'm not completely sure whether this was really number 1, but most definitely within the top 5. Think about it. The most historically important numbers are all here. We have 0 and 1, and then we have pi, we have e, and we have I, all in one. This is really a beautiful theorem. The second application is often called de Moivre's theorem, and I know we have been dealing with this in pre-calculus. If you use Euler's theorem, then de Moivre's theorem becomes really easy because it's nothing more than a exponent rule, because cosine of x plus I sine of x to the nth power is nothing more than e to the ix power times to the nth power. So if you use the exponent rule, then we have, well, e to the inx, and consequently we have cosine of nx plus I sine of nx. De Moivre's theorem. Next, we can express sine and cosine using exponential functions. And we begin with e to the ix power is cosine of x plus I sine of x, e to the negative ix power, and then algebraically manipulate to solve for cosine and sine. We have these two. Please compare these with those of hyperbolic sine and cosine function. There is definite similarity between one and the other.